In the next few videos, I want to talk about membrane potential and just talk sort of broadly about how we might model the electrical activity of neurons and other cells. So, well, what is membrane potential? If you're watching these videos, there's a good chance that you already know, but just to make sure we're all on the same page, if you have a cell, there's going to be a distribution of ions about that cell. So, in general, there is a lot of sodium outside the cell and a small amount of sodium inside the cell. And conversely, there's a lot of potassium within the cell and a small concentration of potassium outside of the cell. And this differential distribution of ions causes there to be gradients, electrochemical gradients. So sodium naturally wants to move into the cell just based off of simple diffusion. Potassium generally wants to diffuse out of the cell. And there's a couple famous equations that you should know to actually calculate what this means for the electrical potential of the cell. And specifically, I'm referring to the Nernst equation. And there's also the Goldman equation, which is basically an extension of the Nernst equation for having multiple ions like this. I'm not going to go into the details of the Nernst equation because I think there's already a lot of sources online, and I'll provide some links in the description to this video. And those of you who have taken, Bio 101 or a course in basic animal physiology, you should be at least familiar enough with this that you can teach it to yourself. So the reason this distribution of ions, such as sodium and potassium, is important is because you build up essentially potential energy. You can think if sodium really wants to flow into the cell, but it can't because the cell membrane is basically a very good insulator. You have a lot of potential energy there, and the way that you think about electrical potential energy is by voltage, and specifically the voltage difference between the extracellular and intracellular. So V is the potential of the extracellular, VI is the potential of the intracellular. The membrane potential is defined to be, we'll call it Vm, membrane potential, is equal to the difference between the internal and external potentials. So this is the definition of membrane potential here, and it's an important variable that is linked to a lot of important cellular events. And if you have an interest in neuroscience, you should know why we would be interested in membrane potential. It's essentially thought to be how neurons perform their computations is by having discharges and dynamic membrane potentials. So we've defined the membrane potential here. In the rest of this video, I just want to quickly tell you a couple important properties of the cell membrane that is going to be important for building a model of the neuronal activity in general and membrane potential. The first point is that the membrane is a good insulator. Membrane equals insulator, and in this, electrical insulator. It's a good electrical insulator. And specifically, I'm referring to the lipid portions of the membrane. They're very good insulators. They won't allow charge through. And that gives the membrane capacitive properties, or it gives the membrane a capacitance. And again, I will provide some links in the discussion or in the description of this video so that you can look up exactly what capacitance means. Capacitance, essentially, very briefly, describes how it's basically the proportional constant that describes the relationship between membrane potential here and Q, which is the distribution of electrical charges. And C here is the capacitance, and that is going to be a constant. And because membranes or cell membranes are good insulators, this capacitance is actually quite significant. So that's the first point that I want to make, that the membrane is a good insulator, and therefore that gives it a significant capacitance. The second point that I want to make is that if the membrane was just a good insulator, then there wouldn't be any changes in membrane potential. But the cell membrane has pores or ion channels within it, which allow the passage of sodium and potassium ions and allows for ionic currents and therefore changes in membrane potential. So the second point that I want to make is that ion channels exist, and they allow for current changes, and these are going to be modeled as resistors. So the ion channels are allowing ions to flow into the cell, and therefore allowing the passage of current to change membrane potential. However, this passage of current isn't instantaneous, and we can model this sort of impeded passage of current as simple resistors. So essentially, the two properties of the membrane so far I've told you. The membrane is a good insulator and therefore has a capacitance, and the membrane also has these sort of resistors built into it. And the third and final important property of cell membranes is that, and I've already sort of talked about this, is that you have ions such as like sodium, for example, are differentially, or I'll just say they're distributed asymmetrically across the cell membrane, and this distribution is maintained by active pumps. So ion pumps such as the sodium potassium ATPase. So ion pumps sort of maintain this distribution of ions, and this gives the potential energy that I was talking about to begin with. So how does all of this, how can we combine these three properties into a working model of the cell membrane? Well, just erase all of this. So if we were designing a circuit, we will say this point here. So I told you that the cell membrane has a capacitance, which in an electrical circuit, this is the symbol that denotes capacitance, and also a resistance. That resistance allows the passage of current. However, there's not just a resistance here, there's this distribution of ions that actually sort of fuels this potential energy, and that can be filled in as a fictive battery. Let's see if I can draw that. So this would be a battery here, and this sets the resting membrane potential, or V rest. So this is sort of the simplest electrical circuit that can describe a cellular membrane, and we've talked about the three components. So the first component here is the capacitance, which just refers to the insulating properties of the lipids in the membrane. This resistor here refers to the ion channels that allow for the flow of current, and the rest here is corresponds to the differential distribution of ions across a cellular membrane. And this is, sort of this fictive battery is kept in place by ion pumps that will pump sodium outside of the cell and potassium inside of the cell. So this simple electrical circuit is what we're going to talk about the next few videos, and in the next video I will show you exactly how we can actually determine what membrane potential is from this. So the membrane potential is, you could take it's basically the difference between the intracellular, which is here, and the extracellular potential here. So the difference between these two voltages gives you the membrane potential, and it turns out that there's a very simple mathematical equation that will give you that.